We now move into designing and implementing an I2C master controller. But before I jump into the design and implementation, I just want to re-emphasize what the protocol actually specifies and what it does not specify. So we know that the protocol specifies how a start condition should look like, how a stop condition should look like. It also specifies the bit level timing, which in other words, it tells us that you should not be changing the data line while the clock is high, or can only change it while it's slow, so that you can distinguish between a start-stop condition or actually a data bit that you're transmitting. However, the protocol itself does not specify the number of bytes in a single transaction. So you can send 2 bytes, 3 bytes, or you can receive 4 bytes or 50 bytes for that matter. So designing a controller that can account for all different bytes is going to be a very, very tedious task. So what we do is, instead of designing something on the transaction level, we're going to design a controller on the action level. And what I mean by the action level is we're going to design a controller that actually generates, for example, a start condition, generates a stop condition, a restart condition, maybe write a byte and check the acknowledgement after it wrote it. It see the acknowledgement from the slave, or maybe reads something from the slave and then acknowledge or not acknowledge, sending it's the end. So these ones in here are basically the basic things that a controller can do. And if you take a look at them, you can construct a whole transaction, whether you're reading or writing 8 bytes or 50 bytes, just by picking some of these actions and assembling them together, or basically combining them together. And we're going to do that using a firmware or a software driver on the variant. So our hardware level is just going to do the basic actions in here, and the driver will be basically picking up some of these to assemble a whole transaction. Okay, this way it simplifies our life a lot. So let's take a look at how these basic actions are actually implemented. And the way we're going to do it is by phases. Each one of these actions will be implemented in phases. And whenever I say phase, I need to specify some sort of a time in here. And the basic of the time in here is going to be the clock. And that's actually not the system clock, but the protocol clock, basically the serial clock, the I2C clock. So any single time now in this particular section here, I say clock or frequency, I mean the clock and the frequency of the I2C protocol, not the system clock. Okay, so we go back to the phases idea. So again, my controller should implement the start condition, stop condition, or restart, and it should actually write or read 8 bits. Okay, so let's take a look at the start, restart, and stop condition. So in here, what we do is we implement them into phases, and each one of the phases for these 3 actions, each one of these phases is exactly half a clock. Okay, so this is half a clock and this is half a clock period. This is half a clock, this is half a clock, and this is half a clock. This is half a clock, and this is half a clock. So let's take a look at how the start condition looks like. We know that the start condition should, while the clock is high, we should take the data to low, because initially they're both at 1, basically, when they're idle. And what we do is we do it in a couple of phases. It's actually phase start 1 and start 2. Okay, so in start 1, we have the clock in high and the data in low, and then we both will have them at low. Okay, and that's how simple it is. That's how a start condition is. Again, the whole thing is now exactly 1 clock cycle. So let me just write this in here. So it takes 1 clock cycle. Okay, so the restart condition is very, very similar to the start condition. But what it does is actually we have some sort of what we call a hold condition, and this actually lasts a very, very short period of time. But basically both of them are at 0, or both of them at 0. So what we do is we artificially raise them to high, and I call it artificially because it's basically artificially making them idle. I'm not artificially putting them at 1, I'm just artificially simulating idle. So in here the clock and the data will be high, it looks like it's idle, and then you basically show exactly the same start 1 and start 2. They're exactly the same because you're restarting. Okay, and the stop condition is also similar. We have a couple clock cycles in here, stop 1 and stop 2. Okay, and you can see how the clock is high and how the data is low in that. And again, we are changing the data where the clock is high, and that indicates that it's a start or a stop condition. Okay, here you will see in the restart condition, I forgot to count how many clock cycles. It's actually half, 1, and 1.5 basically. So I need 1.5 cycle, and in here you can count that it's exactly 1 clock cycle. Okay, again, this is not the system clock, this is the I2C clock. So the restart condition is the only one that takes a little bit over a single clock cycles to actually implement or finish. Anything else you see in here, whether it's start condition, stop condition, or the data, generally speaking, it can be done within, and should be done within one clock cycle. So let's move into not the start condition and the stop condition, but actually the reading and writing. Whether it's reading and writing, you're transmitting one bit at a time because it's a serial communication protocol. But what we do in here in the data stage or the data state, what we're going to be doing is we're going to divide it into 4 different phases. So each one of these data bits or data action, send or receive, we're going to divide them into 4 phases. So because we're dividing them into 4 phases, that means this is a quarter of a phase, this is quarter, and this is quarter. And it's very straightforward. Each one of them is called data 1, 2, 3, and 4, and you repeat it for every bit you want to do, all the way through 9 bits. 8 of these bits are the read and read, and the 9th bit is actually the acknowledge. You do the same exact thing for the acknowledge, whether you're reading or writing. Okay, so what we need to remember is the following. If you're sending or transmitting or you want to write into a slave, what you do is the master should place the new data bit in here at the very beginning of data 1. Okay, and the reason why is because the timing specification for the protocol tells me you cannot change while the clock is low. While the clock is high, so you can only change it while the clock is low, and this is actually guaranteed at the beginning of data 1. And if you're reading or you're receiving something from a slave, basically you should read it between data 2 and data 3, because you know that the data in here is actually stable while the clock is high, and this is basically a stable point where you can read. And you do this again for exactly 9 times, for 8 bits, the ones that you're sending or receiving, and then for an acknowledge bit. And at the very, very end, after all these 9 bits, you actually go through what we call a data end phase, and it also lasts a single quarter of a clock cycle. And basically you just draw down these 2 into zeros, and you go again and you say whether you want to restart condition or you want to stop, or you want to basically send another data byte or whatnot. So the finite state machine that will implement all of these phases follow these graphs really, really closely. So the one that we see in here, it's actually just a straight implementation of these graphs. So let's take a look at it. Again, we are designing the controller on the action level, not on the transaction level, meaning the controller will just basically issue one of these actions, whether it's a start condition, restart condition, or stop condition, or maybe transmit a byte or receive a byte. Okay, it cannot do a whole thing. It cannot do a start and then send the device ID and then read the acknowledge. You're going to have to do this on the driver level. So let's take a look at that finite state machine that actually implements this. It's really straightforward, but we need, before we actually talk about how straightforward it is actually I need to emphasize a couple of things. We have something we call a command, and the command is actually an input, okay? And the input can take several values. These values could be a start command, or maybe a read command, or a write command, or a stop command, and a restart command. You got the idea. It's actually an indication which one of these 1, 2, 3, and 4 or 5, basically, the read and write are different. We're going to distinguish between them a little bit, okay? So it just tells me which one of these 5 conditions that I want to do. So there's an external output that tells me what action I want. And there's also another thing that I want you to pay attention to, which is actually there's apparently a ready signal. This ready signal tells me that the controller is ready to do a new action or a new transaction or whatnot, okay? All right, so let's follow this graph very quickly. So the graph does the following. So an idle state in here, and I'm not showing you the SDA or the S clock in here for simplicity, okay? I'm not showing you how the data is changing or the clock is changing. I just want to show you how it's happening in terms of states or in terms of phases. So when it's idle, if the command is start, what it does, it actually goes in here and implements it in start 1 and start 2, and that's pretty much it. And then you go to something we call a hold condition. The hold condition is only shown in here and here because this is pretty much where you actually see it, okay? And the hold condition is just a state where you stay there for a very, very short period of time. Generally speaking, it is a single clock cycle. That's actually a system clock cycle, not the I2C clock cycle, okay? It's very, very short period of time. You can stay in it as long as you need, okay, till you issue another command. So it's going to be basically, it's okay, I've started, the controller took control of the bus, and now you can actually do something. You can either stop, you can restart, or you can data. But of course, after start, you shouldn't stop right away. I mean, it's like, why would you? So generally speaking, what you do is after the hold, what you do is you issue a command, whether it's a read or write, and what you do is you go through the 4 data here, for data 1, data 2, data 3, data 4, for all 9 bits, and this is basically the 9 bits are generally tracked using bit registers. So as long as it's less than 8, remember from 0 to 8, these are 9 bits. Once you transmit all of them, whether you transmit or write, depending on whether you read or writing, and you read or you asserted and acknowledged or not asserted and acknowledged, at the very end, what we have is we have this data end, and this actually captured in here. It basically lowers both of the bus into 0. After you're done, basically you go back to the hold condition, and in the hold condition you can either read another one, okay, or write another one if you're doing that, or and you can do this basically over and over and over again for like maybe 50 bytes. And this is why I said it's actually easier to do it on the driver level, because the driver would actually send that command in here. But let's say that you send all the bytes, or you read all the bytes that you want. What you need to do after the hold is actually you can either restart, and the restart is pretty straightforward. It actually goes, you assert the command that it's a restart, it goes to a restart and then start. Exactly the same as what we see in the figure in here. Or maybe a stop condition. Basically you want to release the bus, so you go through stop 1 and stop 2, and you release the bus, and you basically are in idle, and another master can take over if that is possible in here. The design in here does not deal with the fact that I might have a different master, so I'm designing a controller for simplicity that doesn't accommodate any special cases. So it does not accommodate multiple masters. We're just going to do a single master in here. So that's how this implementation is pretty straightforward. Again, I'm not showing you the data or the clock. I'm also not telling you the following, that these ones in here and in here and in here and in here and in here actually take half a clock cycle to move between one state to another, as opposed to data 1, data 2, data 3, and data 4, and data end. Actually, these takes 1/4 of a cycle to move. Remember, these ones in here are in 2 and 1.5 and 1.5. Each one of these here are quarter. So whatever you see in red takes basically half a clock cycle. Whatever you see in pink takes 1/4 of a cycle. So how do we know that we have finished 1/4 of a cycle or half a cycle? Actually, we have an external counter that does this. It's exactly just a timer. And the timer is actually tracks the quarters. And because if I track the quarter, I can easily track the halves by a simple shift. And you're going to see it. So a single counter can actually tell me a half a cycle or 1/4 of a cycle.